All right, let's get on with our next set of topics. We're looking at the conservation of mass and the law of definite proportions. Some of these things in this chapter, again, feel like a history lesson, but it's rather fascinating. The things that the scientists in prior centuries were able to do with the limited knowledge and equipment at their resources. In the 1700s, more than 200 years ago, Joseph Priestley isolated oxygen. He didn't quite know what it was at the time, and then he subsequently characterized it by heating a mercury oxide compound. This picture represents exactly that. And he figured out that there was this compound that contained a solid, and as he heated it, a solid and a gas resulted. And there's something special about that gas, and he learned properties of this. But it turned out that there was these two things combining in some way, but you could separate them by heating. The law of definite proportions tells you that when you have one chemical formula, it's always going to be in a certain ratio of its chemical components. And so if there's one mercury and one oxygen, then when you separate it, you're going to get an equal proportion of mercury to oxygen. So if you have 2 on the left, there will be 2 atoms of the mercury on the right and 2 on the right. Now, Priestley didn't know about atoms at the time, this is for sure. But the amounts of them was always going to be in fixed and definite proportions. So here's another example of how definite proportions work. If you take known amounts of 2 solids shown on the left diagram, they look like white powders, which is so typical. So many things tend to be white powders. And one is solid potassium iodide, and the other one is solid mercury nitrate. You weigh them out and put them in water, and you mix them up. The water solutions are mixed together, and you get something very different, something with mercury and iodide results. And you can take that solid from that water solution, an aqueous mixture, and remove the water by evaporation, and you end up with a solid. One of them is solid potassium nitrate, and the other one is what you removed by filtration first is the mercury iodide, the reddish, intense colored compound there. Now, how does this reflect definite proportions? Well, let's think about it. The amounts of the potassium iodide and mercury nitrate were weighed out before they were combined. The mercury iodide was weighed out after it was dried, and so is the potassium nitrate. So on weighing, the combined masses of the products equal the combined masses of reactants. Let's look at the actual data for an experiment of this type. This demonstrates the law of conservation of mass. What is it? Mass is neither created nor destroyed in a chemical reaction. It's always got to be somewhere, and sometimes we haven't accounted for it successfully, but it's always got to be there someplace. And so we try in our chemical reactions to do our best to verify that we haven't lost anything, and representing things carefully. So the mercury nitrate and potassium iodide would be these 2 compounds on the left that are combined, and here are the masses of the things that they combine. So 3 and a fraction grams of one and 3 and a fraction grams of the other. A total of 6.57 grams were combined, added into water solutions. When there's aqueous solutions, means it's in water. I hope that sounds logical. The product resulted, and that is the mercury iodide, which precipitates. That means that it is a solid. The solid is something that makes a very distinct layer at the bottom of a solution. And the mercury 2 iodide and the remaining solution contained the potassium nitrate. When it was evaporated and the mercury iodide was collected, you could find the masses of the substances that were collected. So the mercury iodide was weighed out, the potassium nitrate was weighed out, and what do we know? If we've done our experiment carefully, and it's not always easy, of course, the masses of the reactants should equal the masses of the products. In fact, this one was done carefully and successfully to verify that mass was neither created nor destroyed in this particular chemical reaction. Things are going to occur in different ways, specific ways to help that to happen. But the law of definite proportions goes on from here. And so, if I can advance the slide. The law of definite proportions takes this a little bit further to tell us that samples of a pure compound always contain the same proportion of elements by mass. What do we mean by that? Well, let's think they're going to combine in specific ways, but not random ones. So let's think about water. Everybody's heard of water, I suspect, and it is known by the formula H2O. And if you didn't know back in the days of Joseph Priestley, you couldn't always say what was in it, but you could characterize it. What you would find out eventually is that the percentage of water being oxygen is always 88%. Doesn't matter where you find it. And the amount of hydrogen is always 11.2% by mass. Now, using our periodic table today, we know why that works, because there's 2 hydrogens for every oxygen, and each of them have specific masses. But no matter what, when it's water, you always have this specific proportion by mass when it combines. So that's what we call the law of definite proportions. It has to do with the fact that there are 2 hydrogens, for sure, here in water for every oxygen, and the mass of oxygen is so much greater than that of hydrogen that there's 88% oxygen. You will have examples to practice with this concept on Mastering Chemistry. That would be the end of this section. I will stop the recording here and resume with a new topic.